Hi, I'm Armand, and I'm the founder and CEO of General Proximity. General Proximity is solving the biggest challenge in drug discovery, which is that there are many well-known drug targets that we understand the biology of in disease, but where we lack the technology to effectively modulate that target in a human. The way this changes is that some new technology comes about, and suddenly the undruggable becomes druggable. So we are developing a fundamentally new class of medicines that we call next-gen induced proximity therapeutics. At very high level, they work by inducing protein interactions or proximity events between two proteins in your body to drive some effect. Why is this so powerful? Essentially, all biological phenomena are downstream of binary protein interaction events, meaning any biological output you can think of is on some level controlled by two proteins interacting. And so if you can understand that interaction landscape, you suddenly gain the ability to control it and drive biology that isn't possible to achieve with any other modality. This is what we built our tech around. We pioneered this space. We built a set of platforms that allow us to understand for a given drug target which protein interaction events drive the biology that we care about. We've applied our technology to only the most high value targets we could find beyond just having platform disease fit. Does the target make sense for our technology? The only other major criteria we use to pick targets is that do we think this program could eventually impact all humans on Earth? Because of that, we've generally worked on transcription factors. Transcription factors are a class of proteins that are at the root of all health and disease. They are canonically hard to drug or undruggable, yet all transcription factors are controlled, even more so than most other proteins, by proximity events. A given transcription factor will have hundreds or thousands of protein interactions that orchestrate and tune every level of its function. So if you can understand the proximity landscape of a given transcription factor, you suddenly gain the ability to tune its biology in ways that you couldn't do before. Our flagship program is for the most important target in oncology, the master tumor suppressor in humans, a protein that controls all major tumor suppression pathways that's never been drugged. We have made, to the best of our knowledge, the most potent activator of this target ever created. We plan to put our first molecule from that program into humans next year. Beyond that, we've worked on a number of very interesting targets in neuro, cardiometabolic, and longevity. There are all sorts of very powerful outcomes you could get by modulating transcription in things like longevity. For example, mitochondrial biogenesis, cellular resilience, metabolic adaptation, autophagy, cellular reprogramming. All of these things are controlled by transcription. We've got a number of programs in this space that we're advancing towards the clinic as well. We've raised about $25 million to date from some of the best investors in Silicon Valley and beyond. We've received major grants from the National Cancer Institute and ARPA-H. And we've also just recently announced our first platform collaboration with a major pharma company, Daiichi. They're paying us to use our technology to go after some of their high-value internal targets. We're getting ready to raise our Series A in the very near future. If you'd like to learn more, you can check out General Proximity at prox.bio, prox.bio, or you can email me at armand@prox.bio. Thank you for listening, and thanks to the Long Game folks for putting this on.
So a couple comments there. Hey, well done. Very smooth, and you've been executing like a madman. So we're proud to be on the cap table. We have a broad audience on the call. So just by way of background, the induced proximity, pulling together proteins rather than the typical pharmacology of enzyme inhibition or activating receptors, sometimes called molecular glues and related all kinds of subtypes of the space are coming out. Rapamycin, which is the best known longevity drug, is an induced proximity drug. It pulls together 3 proteins, not just 2. It's kind of amazing that natural products evolution that can achieve that. So just to kind of highlight, you've got a great cap table. You have Felicis, Y Combinator, H1, Jeff Dean from Google AI, Wilson Sonsini, the law firm, a bunch of prominent angels, and you also got a $3 million grant from ARPA-H recently, and some golden tickets, BMS, Astellas, AbbVie, and other pharma. So absolutely crushing it. And just speaking about, I don't know if you want to elaborate on P53 as a target. This is the guardian of the genome. It's the most studied gene in the entire genome, full stop. Fixing P53 mutations in cancer, it could apply to many different types of tumors, sort of a holy grail target for pharma. So why is it so hard to drug? It's unstructured domains, transcription factor, and how have you guys managed to get a handle on it?
Yeah. So first of all, thanks for that really nice intro. And yeah, P53 is just such a fascinating target, and it's not just an oncology target too. It's also an aging target. Controls DNA repair. So we're definitely, as we look at it, we're looking at things beyond just oncology for the long run. But for the oncology aspects, so P53 is the canonical tumor suppressor in humans. As a consequence of that, it's like tautological that it has to break for cancer to form, because it's functional. Cancer cells just don't really thrive. So it's broken in almost all cancers. And generally speaking, most small molecule drugs are great at breaking things. They're usually inhibitors, like you mentioned. They're not really good at fixing things. That's why more complex therapies exist, but many of those don't really work in cancer for various reasons, like delivery. So it's just been this target where the technology didn't exist, and there's a massive amount of failure. It's a very well-known target. People failed for many decades, and kind of pharma, said we can't do it. But really, it was just the technology to drug P53 didn't exist. And so the reason it made so much sense for us, despite all the failure, is that, again, it's a transcription factor. And the way transcription factors work is that they sit in the cytosol of your cell, and some protein will come in and interact with them. Based on that interaction, the transcription factor will go to the nucleus and induce a specific transcriptional response. Any transcription factor has many different responses it can induce. So basically, P53 has hundreds or thousands of interacting events that tune its function and turn on different tumor suppression programs and other things. So we thought, look, if that's true, if P53 is controlled by protein interactions, it's probably much easier to rescue its function in cancer with a protein interaction compared to what people tried in the past, which is just a small molecule interaction. So that's basically what our platform does. Is it says, for a target like that, can we find the right protein interaction, first of all, which is a very non-trivial problem. That's what we build all of our tech around. Once we've done that, we can make a drug that induces that interaction, and then can be used. And it's a small molecule, but just much, much more powerful than like what you could get with a traditional small molecule.
Rock and roll.